Okay, so we're going to look at a couple of additional situations and strategies with U-substitution today. In the previous video, you kind of got the basics of how to apply U-substitution, and so now we're going to look at just some sort of extra what-if kind of things. You might hear the new kitten in the background because he's bopping around like a crazy person. And you might hear my coffee pot going in the background because I got to keep the fuel going for this snow day. So sorry for the background noises here at home. So for number 9, these are both examples of kind of an abstract representation of U-substitution. So remember, the integral, what we're doing is the antiderivative. So the antiderivative of f prime is going to be f. You're undoing the derivative. But because there's the 3x on the inside, that tells me, like, if this was a derivative, I would need to use the chain rule. So whenever your integral feels like the chain rule, that's how you know you need to use U-substitution. So in this case, I would let u equal 3x because that's what's on the inside of my function. Then du is going to be 3 dx. That's the derivative of 3x. And I have a dx, but I don't have a 3. So what we talked about yesterday is I can multiply by 3 on the inside wherever I want, as long as I multiply by 1/3 as well, because that really cancels each other out. So we're not changing the value. That's just multiplying by 1. So when we apply our U-substitution, then we're going to get 1/3. That's what's left over. F prime of u, because that's what we defined 3x to be. And now this 3 dx is what du is equal to, so I can plug that in. Now I'm going to have 1/3 times f of u plus c. F of u is the antiderivative of f prime of u, okay? Now, one thing I'm noticing is some people are still leaving the integral symbol here. When you take the antiderivative, you've used it. It's the same as saying like square root of 4 is 2. It's not the square root of 2 because we've used the antiderivative symbol. We've applied it. So it shouldn't be there anymore in your final answer. And again, to get this back to what we started with, now we're going to put our u back in. So I get 1/3 f of 3x plus c. And because we don't have any more information about the function f, like that's just our answer in abstract form like that. Okay, so take a second to pause and see if you can try number 10. It's going to be a very similar process. I'll come back here in 3 seconds with the work for it. Okay, x squared plus 2 is what's on the inside of our function g double prime. So that's what we want to let u be equal to, which gives us a du of 2x dx. The swap here, when we substitute, should give us 1/2 g double prime of u du. Again, the 1/2 is because I need a 2 in my dx, so I can multiply by 2 and multiply by 1/2. The 2 gets used inside the du, but the 1/2 doesn't, so we just leave it on the outside of the integral. And so this would be 1/2 g prime of u plus c. We undid one of the primes. And so our answer is going to be 1/2 g prime of x squared plus 2 plus c. And that's what we should get there. Okay, let's look at a couple where we have to use more than one substitution. This is kind of when your U-substitution gets a little wonky. I told you in class or in the previous video that we can adjust for constants because of the constant multiplier rule. If I have an extra 1/2, I can bring it to the outside of the integral to multiply. You can't do that with a variable. I could multiply by x over x, but I'm not allowed to pull a piece out of the integral because x is not a constant. It would have to remain on the inside to be used with your substitutions. So here's an alternative to that, okay? So number 11, if you set this up the way that you feel like you should, it's pretty straightforward. I'm going to get u is equal to 2x plus 1, and du is going to be equal to 2 dx, okay? Yes, that's right. Okay, now I can see I've got dx and dx. I need a 2. That's easy to take care of. I'll multiply by 2 and multiply by 1/2. That gets me my 2. U is 2x plus 1. But here's the problem. I have this x left over, and nothing over here tells me what x is equal to be able to substitute. But we have this relationship that U is equal to 2x plus 1. What that allows us to do is rearrange this. I can subtract 1 and divide by 2, and it tells me that x is equal to U minus 1 over 2. So when you have kind of this extra variable left over, rearrange your U equation. Once you've labeled that to be true, any reorganization of that equation is going to also be true. So we can use both. So what that allows us to do then is to set up our integral like this. I have the 1/2 that I adjusted with my constant times the integral of U minus 1 over 2, that's what I'm plugging in instead of x, times the square root of U, which is going to be U to the 1/2 du. Now I have to do a little bit of algebra here to figure this out. This U minus 2 or U minus 1 over 2 is the same thing as 1/2 times U minus 1. So I can bring that 1/2 out and multiply it by the constant multiplier I already have. That makes it 1/4. Then in here, I have U minus 1 times U to the 1/2 du. And so I can distribute this U, and remember when we multiply, we add exponents. So what I'm going to have now is 1/4 times the integral of U to the 1 plus 1/2, which is 3/2, minus 1 times U to the 1/2, which is U to the 1/2 du. And now we can integrate from here simply using the power rule. Now the 1/4 is times your entire answer. So we're going to have two terms when we integrate, so parentheses are really important here. We're going to get U to the 5/2 times 2/5, add 1 to the exponent, divide by 5/2, which is multiplying by the reciprocal, minus U to the 3/2 times 2/3 plus C. Okay, now the parentheses can include the plus C. They also don't need to, because the idea is this. If I distribute now this 1/4, okay, 1/4 times C, where C is any constant that I have, 1/4 times a constant is still just going to be another constant. So we're still just going to call it C, because it's any constant you can imagine can be C. So 1/4 is still going to be any constant we can imagine. So when I distribute here, notice the 2's on top are going to simplify 2 over 4 to 1/2. So what I'm going to get is U to the 5/2 over 10. 2 over 4 is 1/2, and 1/2 times 1/5 is 1/10. Minus, for the same reason, U to the 3/2 over 6, plus our arbitrary constant C. And now we can plug back in what we had for U, which is 2x plus 1. So this is 2x plus 1 to the 5/2 over 10, or times 1/10, it's preference. 2x plus 1 to the 3/2 over 6, and then plus C. And that would be your final answer. All right. Number 12 is going to be very similar. You're going to have to use a secondary substitution to take care of this extra x. Now, when you read this, and this is just something you have to get used to reading correctly, you see how all of this is smushed together right here? That tells you that this is a cube root, not an x cubed. An x cubed times a square root would very clearly be separate. There would be a clear space between them. Whenever they're all smushed together like that, you can assume that the cube is attached to the root. So it's not an x cubed, it's 3x times the cube root of 4 plus x. So pause your video and see what you can make of this, and I will come back in the work in 3 seconds. All right, here's enough to get you started. So U is equal to 4 plus x. That means du is equal to just 1 dx, or just dx. And then if I look at what I have here, all I need for du is a dx. I've got that. That means this 3 here, I don't need it. It's not, I don't need to adjust. I don't need to make it a 1/3. I don't need it. So I'm just going to pull it out to the front of my integral off to the side. And then because of this x that's left over and I don't have any x's in my dx, I'm going to need this substitution that x is equal to u minus 4. And so we get the integral in green after we substitute. If you were not able to finish, pause it and finish this out. But I'll go ahead and finish this for you now. All right, hopefully you get to here, and then we just need to do some simplifying. Now, the second one is really nice. The 3/4 cancels out the 4, and the 3/4 is from dividing by the new exponent 4/3. And so now when I distribute, we're going to get 9/7 u to the 7/3 minus 9 u to the 4/3 plus c, and now we can put our u back in, which was 4 plus x. So 9/7 times 4 plus x to the 7/3 minus 9 times 4 plus x to the 4/3 plus c. Okay? All right. Now, for this last set, if you can't use U-substitution, then we have to try to find some other algebraic method that we can rewrite the integrand. Now, we have seen some of this already. So that's good. Now, for number 13, we've seen derivative problems like this. We've seen integral problems like this already. So this is just a reminder that this is an option. If you have a monomial divisor, then we can go ahead and divide that out term by term. There's two different ways to think about this, okay? I can think of this as 1 over x to the 1/2 minus x over x to the 1/2. Break apart that fraction. Or you can think of it as 1 minus x times x to the negative 1/2. Whoops, 1/2. Because that's essentially what we're doing by bringing the x to the positive 1/2 up to the denominator, or to the numerator, sorry. Then you could distribute here and go from there. Or if you do it this way, then you're going to divide and rewrite each of these things. My brain sees it the first way, but I know a lot of people like the second way better. It doesn't matter how you think about it. You just need to be able to get there. So when you rewrite this, we would get x to the negative 1/2, that's 1 over the square root of x, minus x to the positive 1/2 dx when you simplify. Either one of those ways, distributing the x to the negative 1/2 or dividing each by x to the 1/2, should get you to this, okay? I'm just going to, for now, say ... From here, you can check the rest of the work in the PDF that's posted on Canvas, but let's just focus on setting these up so this video doesn't get too long. Number 14. Now, this one looks like it has an inside, so you may think that you want to do U-substitution. It's not going to work, but let me show you why. So don't copy this down, but this is why. When you have u equal to x squared plus 1, then du is equal to 2x dx. I can get a 2 in here. I can multiply by 2 and multiply by 1/2. But like I mentioned before, I can't do that with an x. I can multiply by x over x, that's fine, but I can't pull that x in the bottom out to the front and hold it off. So that gives me an extra x to worry about that I can't really do anything with. So we don't want to do that, okay? So U-substitution here is just going to make a mess. What we can do instead is go ahead and multiply out this binomial. Squaring a binomial is easy. Square the first, square the last, multiply and double. So this becomes x squared squared, which is x to the 4th, square the first, square the last, we're going to get 1 squared, which is 1. Then we multiply these two together and double it, so 2x squared. And now that's just power rule. That's an easy one to do. So again, I'm going to ... this. You can look it up yourself. Number 15 is one where using some division is useful, okay? If I have x squared plus 3x minus 4 over 2x plus 2. Now, I can't really do much with this in its form right now, but I do notice that I can do some factoring here. And we saw with limits and with derivatives that if you can factor and simplify first, you can make your life a lot easier. So I have the integral of x plus 4 x minus 1 over 2 times, x minus 1 dx. Then we can see that the x minus 1's divide out. I also have, this is essentially 1 over 2. It's a constant multiplier, so I can pull it out. So I get 1/2 times the integral of just x plus 4 dx. And now that's going to work a whole lot nicer. You wouldn't find a U-substitution arrangement that works well on that one, so that's not going to work. So that's kind of how you would want to set that up. See if you can factor and if you can simplify there. Now, even if it's not factorable, let's just think of a little side note here. What if it was just x minus 2 on the bottom instead? Let me write this in a different color because this is a different problem. Okay, so let's call this 15b. What if this was x squared plus 3x minus 4 over just x minus 2? Okay, we saw from factoring above, x minus 2 isn't going to be a common factor that divides out, but we can use long division, or we can use synthetic division in this case because it's an x minus c factor, to divide this out. So we would put 2 on the corner. Our coefficients are 1x squared, 3x, and negative 4 is the constant. Okay, remember how to do this. You bring the first one down, then you multiply 2 times 1, that gives me 2, and then you add, which gives me 5. I multiply 2 times 5, that gives me 10, and I add, which gives me 6. So that means that what I get when I divide, you go 1 degree lower. So I started with a squared. I'm going to start now with a first power, x plus 5 plus 6 over x minus 2. So now we can use that as our integral. The integral of x plus 5 plus 6 over x minus 2 dx, and you can go from there. Now, we'll talk about this a little bit more when we get into the log rules in the next section, but you saw already that the integral of 1 over x is natural log of the absolute value of x plus c, dx in there. So you can use U-substitution on this piece and use the natural log. So you're going to get x squared over 2 plus 5x plus 6 times the natural log of x minus 2 plus c is how that would work. That's kind of something to hold on to for later, but that is a strategy. Any algebra tools that we have are going to work here. Number 16 is just like number 13. You can either divide or write this as x to the negative 1 and distribute it and go from there. So I'm going to leave that as an exercise for yourself, and we're going to call that good for today.